Welcome back to Physics Fundamentals. In this video, we're going to be talking about wave motion. When you think about waves, most people immediately start thinking about water waves in the ocean. And that's certainly not a bad place to start, but it's far from the only type of wave that exists. In general, a wave is a traveling oscillation. Waves are closely related to simple harmonic motion. To see what I mean, let's jump over to a simulation. It looks like we're on Mars or something because I didn't want the bright white screen to be behind me. And let's go ahead and start this motor running. And as the motor goes, right, and that's just simple harmonic motion. In this case, it is a motor, but it could just as easily be a mass on the end of a spring for how it's behaving. And that motion causes a bit of a motion in the string attached to it, which continues onward, and without any other effects trying to counteract it, that motion will continue onward forever. A little bit of vocabulary here in this simulation. I have two controls over here for amplitude and frequency. The amplitude of a wave refers to how far away from the center line do the peaks fall. So if I crank up the amplitude, whoops, there we go. If I crank up the amplitude, you can see that the waves get to be a lot taller. And if I bring down the amplitude, the waves become quite small. The frequency is how fast the wave is propagating. The frequency of a wave like this is very closely tied to the period of a simple harmonic oscillator. So currently my frequency is at 2 Hertz. If I crank up the frequency, it's going to cause the wave to move a lot faster, which causes the individual waves themselves to appear a lot closer together. That is really awkward to gesture to, sorry about that. And then if I drop down the frequency, it causes the waves to spread out and slow down a little bit. All right, let's put this back at something a little bit easier to see. The other controls that I have on this particular simulation have to do with damping. Right? In general, if I set up a wave generator like this, it's not going to be this nicely behaved. Right? If I start shaking a string, it's not going to continue onward indefinitely like this. In fact, the first couple of bits where I shake it are going to look pretty nice, and then after not too much distance, it's going to start to settle down and fall out. Another thing is that this string is set to continue onward indefinitely. That's also not something that usually happens. In reality, we usually have to do something on the other end. We can do something in the form of having the other end able to oscillate on a fixed post, or we can just, completely eliminate the other end and force it to stay in one place. There's a lot of control we can do with all of that that is not really all that interesting for us in this course. So we'll stick with the simple picture of no damping, string goes on forever, nothing weird is happening, and the wave behaves fairly normally. A little bit more vocabulary of waves. If I go ahead and just trace out, let's try a little bit nicer. That's a little bit nicer. All right, this is one period of the wave motion. Just like when we talked about simple harmonic motion, if we think about just what's happening vertically, the wave goes up, the wave goes down, the wave comes back, and when it comes back to where it started, that is one period. In order to talk about it like that, I'm assuming that this horizontal axis is representing the elapsed time, right? So as time continues, the time it takes for the generating point or for any one point on the wave to go up and down and back is one period. Coming back over to my simulation, all right, let's pick this blue dot as it goes up and down and up and down. So we're looking at this blue dot as a simple harmonic oscillator and talking about its period the same way we talked about the period of a pendulum or the period of a mass on a spring. The other thing that we notice is, well, let's grab one of these troughs because it's something I can point to. Right? The trough itself moves across the screen, across the world. So if I go back to my notes sheet, and instead of talking about this as time, if I start talking about this as space, so that's the x direction. In this circumstance, we're going to call that distance the wavelength. And the variable for wavelength is almost always a lowercase Greek letter lambda. Because L doesn't quite make sense, it's not a physical length, it's a length of something that is a little bit more ephemeral. All right, one more quantity here is the wave speed. All right, so if we pick a specific point on the wave, usually a crest or a trough of the wave is the best place to talk about that. The speed at which that crest or trough moves as the wave propagates is called the wave speed. And then the last bit of vocabulary we talked about the frequency of a wave, and mathematically a frequency is literally just 1 over the period. Right, so the variable for frequency is almost always f. The variable for period is still capital T. And so our units here, right, so if I have a period of 3.50 seconds, then the frequency is going to be 1 over 3.50 seconds. My calculator is happy to tell me that 1 divided by 3.50 is 0.286. And then my units are 1 over second. Because this 1 over second happens so often, it was worthwhile to give it its own name. And so the 1 over second unit is called the hertz with variable hz. Something interesting that comes up from this. If I have a wavelength of, let's say, 0.750 meters, right, a 75 centimeter wavelength, which is probably reasonable for a small experiment happening on a desk. My wavelength has units of meters. My frequency has units of 1 over second. So if I take lambda times f, wavelength times frequency, well, in this case I get 0.214, but the interesting thing here is the units. I have meters. I have hertz, which is 1 over second. Combined, those units are meters per second. and that is the wave's speed. Right? The variable we're going to use for speed in this case is u, because again, it's not physically an object moving. So it doesn't quite make sense to use the same v for speed that we've used for everything else. And in fact, one of the interesting research questions, one of the interesting things to analyze when you're looking at a wave is how fast is an individual particle moving as the wave goes through. That's actually something that I have done active research on, specifically in the case of a tsunami, but in general in water waves. If you are looking at water waves passing through and looking at the amplitude of the wave and looking at the wave speed, how does that relate to the speed of an individual particle of water that has to move around as the wave passes through? So the speed of an object, the speed of a particle, is going to be v. The wave speed has to be something else. We use u for that instead. All right. One last thing about waves, if I can hit the right buttons. There we go. All right, and so jumping over here, there are two forms that a wave can take. The model that we've been looking at is what's known as a transverse wave. So this model, like an ocean wave where things go up and down, is a transverse wave. Another is a longitudinal wave. I've also seen these called a compression wave. And if I go ahead and hit play on this, we can see that, well, what's waving? You have bits of the particle that are squeezed close together, and you've got bits of the particle that are spread far apart. If I play around a little bit with the amplitude of these waves, you'll see that as the amplitude goes down, right, for the transverse wave, that means things are getting flatter and flatter and flatter. For the longitudinal wave, as the amplitude goes down, notice how the difference between where it's spread out and where it's close together has changed. And then if I increase the amplitude, we'll get the peaks where things are closer together more and more until you can get to this point where it feels like you've got this solid line because you've got bits that are so closely packed together. Right. That sort of a longitudinal wave is incredibly common and incredibly useful, especially in things like sound. A sound wave is a longitudinal wave. We'll be talking a lot more about sound in the next video, but for right now, just as an introduction, that's a thing that can happen. Right. I think that I introduced this saying this was the last thing I want to talk about, but there is one other thing that I want to talk about, actually two other things that I want to talk about. They're both relatively short because there's not a lot I can do with them. The first one is superposition. The idea of superposition has this mythos about it in popular science. A lot of people will read discussions of science and convince themselves that superposition is a very complicated thing. Because in quantum mechanics, there's a lot you can do with superposition that is really strange. But at its basics, superposition is one of the most straightforward ideas in physics. Superposition says if two waves overlap, well, that's not what I wanted to say. If two waves overlap, add their amplitudes. So if you have a wave and you have another wave that's doing a slightly different thing, And let's emphasize the center line here so we can see a little bit more clearly what's going to happen. All right. Well, point by point, you've got a lot here, positive and negative. And right here, they're going to cancel each other out. But eventually you get to where there's more positive than negative. Which gives you some curve that looks like this. And then you get a lot more positive than negative. So this is going to start going upward before it peters back out. And then over here, everything is negative. Oh, I'm having a lot of difficulty drawing this, but that's okay. All right, one of the interesting things that should happen is whenever one of these waves goes through zero, the red line should be right on top of the other wave. All right, so that's a very terrible line, but that's the basic idea. This technology, among a number of different places where it is used, is the foundation of noise-canceling headphones. So, the idea is that we're going to put a microphone on our headphones, on the outside of the headphones. And that microphone is going to pick up all of the sound waves that are happening outside of your headphones. And then we're going to add to the signal that we are creating with the speakers in the headphones the exact negative of that original wave. So that when you take the superposition, adding them together, you get nothing or almost nothing. And again, as with so many of the things that we've been talking about, there are a number of other things that you can do with this information. For right now, I just want you to be familiar with the basic vocabulary. And last, certainly not least, let's go back over to that original simulation. And what I want to do is just play around a little bit with the frequency here. That's not the button I wanted to hit. Sorry about that. Okay, there we go. That's going pretty quickly. And if I've set this up correctly, and I don't think that I have, that's okay. When you have a wave like this that is clamped on one end, what ends up happening is the wave comes in and then bounces right back out. And that is going to cause the wave to interfere with itself, and you get superposition with itself. If I can set this up just right, and I'm not sure if I'm going to be able to because I don't have time to really play around with this simulation the way it deserves. But if I can set this up just right, I can get that interference, instead of destructing with each other, to become constructive. Well, there we go. That's looking a little bit more like it. Where instead of dying off, the waves start growing on each other, and you end up with this thing that is just bouncing and becoming more and more and more instead of becoming less and less. All right. So this is an idea called a standing wave, and standing waves are themselves very important in a lot of applications of sound. A standing wave is how something like a guitar or a piano works. by plucking the string and causing a standing wave, causes the string to vibrate at a certain frequency, causes the air to vibrate at a certain frequency, and then you hear the sound. Right. These are things to look forward to studying in the future. We'll talk a lot more about sound in the next video. But for right now, I think I've thrown enough at you, so I'll wrap up with that. As always, thank you for joining me, and I'll see you next time.